I was born in Cleburne, Texas, Johnson County. Grew up son of a preacher. The first house that I kind of remember living.
All right, are we rolling? Good deal. Do I have any students this morning? That's the other question. All right. Oh, I'm assuming so. Good morning, guys. So I'll get my hands on your schoolwork from last week today, and I'll start getting those graded. So keep up the good work. We're going to spend this week working on word problems, which I know is everybody's favorite. So we will get through as much as we can together, and I'll do what I'm wanting to do is to set them all up with you guys, and just so that you can be familiar with the terminology of word problems, and I mean using trig to solving word problems like is pretty practical, and you'll see like it gets used in a lot of different fields professionally. So let's just dive in. So we are on page 409, I believe. No, 403. Put my glasses on so I can see. 403. So what we're going to do today is just read through some word problems and just work on setting them up, okay? We're not really going to solve for anything. We're just going to get familiar with some of the terminology. So let's just read through some of these scenarios, and then we'll take this and we'll apply it to some problems. So I'll let you read on your own time the paragraph, the introductory paragraph. It's just basically saying trig is used for a lot. Surveying, navigation, construction, aeronautics, like trig is very practical. And so let's just go through table D. I don't want to spend too much time on this because I actually want to go through the problems with you. Your chore is to stay with me, do what I do, and absorb it, okay? And then turn it in, okay? And then that way I'll know that you were actually with me, working with me and listening and absorbing the information. So these are, it says table D, common situations. So here's some wording and just some application, and then what that looks like when you use a right triangle to solve for whatever. So the first one is perpendicular to. So it says that the branch of a tree is perpendicular to the trunk. So let's say this is the tree, this is the trunk of the tree, and here's a branch. Okay, here's your tree. So this would be the branch. if it's perpendicular to, that means that we know it makes a 90-degree angle. So if I just close that up, I've just made a right triangle. So given a little bit more information, we could find some unknown part. Okay, so it'll make a whole lot more sense once we dive in. Okay, so here, given a right triangle, the next word is height. A bird is flying at a height of 30 feet. So that would be up here. This would be my bird. And this would be the height of this right triangle. Okay, the next one has length or distance traveled from the base of a tree. Here's the scenario. A turtle walked away from the base of a tree for 10 feet. Okay, that would be this thing right here, right? This would put the turtle here. This would be the base. This would be my tree. So I would be looking for that. All right? Just kind of common sense. The next one, an angle of 30 degrees. So here's a possible scenario. A wire made an angle of 30 degrees with the ground. Okay? So this would be the ground. This would be the wire. This would be my 30-degree angle. Okay? And last one, here is a term, angle of inclination. So if I was told that that angle of inclination is 50 degrees, I know that this is talking about this one, okay? Hopefully you hear the word incline in the word inclination, okay? So that would be the degree that it inclines. So that would be referencing this one right here, okay? So that was really fast, I know, but really it's just kind of common sense, okay? So I just want to make sure that we have enough time. I would love to be able to set up all of today's problems with you, okay? So that was rapid fire, I know. Really early in the morning to be talking that fast. Okay, so turn the page. Oh, well, there's an example. So let's just read through the example. Example 8.4a says, okay, so here are your instructions, and this is what we're going to be doing today. Draw a reasonably accurate right triangle to represent the following situation. Do not solve. Okay? So we're not going to actually be using sine, cosine, and tangent today. Today we're just going to practice setting up right triangles. So here's the scenario. So be reading with me. I'm on example 8.4a. The angle of inclination from the bottom step of the Lincoln Memorial to the top of the Washington Monument is 7.5 degrees. The Washington Monument is 555 feet tall. Find the distance between the Lincoln Memorial and the Washington Monument round to the nearest tenth. Okay? So you can see the, our marker's dying. So this would be the Lincoln Memorial. This would be the Washington Monument, and we know that it's 555, I believe is what it said, 555 feet. And we know that there's an angle of inclination of 7.5 degrees. Okay, so that's how that would be set up. The question is find the distance between the Lincoln Memorial and the Washington Monument. So this right here, this side of the right triangle represents the distance between the two. So I would do this, okay? So given this angle, I have opposite and adjacent. So if I were to solve it, I would use the tangent. The tangent of 7.5 equals 555 over x, okay? Pretty simple. So let's dive in. Okay. A little tidbit. Let me just draw this to your attention. This is common sense as well. But on the bottom of page 404, under example 8.4a, it says, once a right triangle is drawn, use the Pythagorean theorem and trig functions. Oh, thank you so much. This one's petered out. Use the Pythagorean theorem and trig functions as needed to find the desired information. Check your answers that fit the context of the problem. Remember that lengths or distances cannot be negative. So if you're using the Pythagorean theorem and you're either solving for A, B, or C, it doesn't matter. You're going to have to square root whichever it is. You're going to end up with plus or minus. Obviously, we don't use minuses. There are no negative lengths. They are always positive. So that was just a reminder about that. So now turn on over to page 408. So today's assignment is 8.4a on page 408. And we're going to work on numbers 1 through 8. Okay, so today all we're doing is setting up the triangles. Okay, we're not actually solving them. So let's read the first one together. A 20-foot ladder is leaning against the roof of a house. The house is 13 feet tall. How far is the base of the ladder from the house? Okay, so to give you a very detailed picture of what's going on, let's say here's your house. Okay, and I know that there is a ladder leaning against, okay, here's the ground, and here's a ladder. This is my ladder. Do something so you can see the rungs. Here's my ladder leaning up against the house, okay? Now, it says that it is a 20-foot ladder, so I know that this ladder is 20 feet long, and I know that the house is 13 feet tall, so from here to here is 13 feet. The question is, how far is the base of the ladder from the house? So I would be looking for that, okay? So hopefully you can see a right triangle in here that we can extract. Yes?
We want to know if they need to be writing questions down.
Oh no, these are like paragraph long questions. No. Thank you for asking. So hopefully in here you can see a right triangle that we can extract here. All right, so just looking at the right triangle, 13 feet, 20 feet, and this guy would be an X, okay? So this is the ultimate answer that I'm looking for, okay? And I also want to see your units, okay? If it's an angle, please give me a degree symbol. If it's a measurement, please give me the units. And then also, like, I need to see what it is that we're looking for, so make sure that you give me an X as well, okay? So we're done with this problem, but if we were to hypothetically say we were having to solve the problem, I would use the Pythagorean theorem, okay? A squared plus b squared equals c squared, and then I could figure it out. I could figure out how far the ladder is from the base of the house, okay? So hopefully that makes sense to everybody. Let me know if it doesn't, all right? So let's tackle the next one. All right, so number 2, let's read number 2. All right, a marching band is practicing in their school parking lot. They start out heading north and they walk for 32 yards, and then they turn east and they walk for 18 yards. How far away are they from their starting point? Okay, so here's my starting point. That's where they started. And it said that they walked north, so we know on paper that's up, and they walked for 32 yards. So they went north 32 yards. Okay? And then they turned east. So we know on paper east is to the right. So from here, they turned east. And they went for 18 yards. I know that my 18 looks about as long as my 32, but If you've been in geometry, you know to go by the numbers, you never go by the picture, okay? So the question is, how far away are they from their starting point, okay? So this is where they're at now. So how far are they from here? Well, all we have to do is draw a hypotenuse. And the question was, how far are they to their starting point? So we would be looking for the hypotenuse. We'd be looking for C. So again, if I were to solve this, I would use the Pythagorean theorem. Do a squared plus b squared equals c squared, okay? Now, the importance of putting your units in on your measurements is to make sure that one of the reasons is to make sure they're the same, okay? Because if this had been yards and that had been feet, we would have had to have done some converting, okay? We can't mix the two. So lucky for us, they're the same, all right? So, everybody still good? If so, we will continue on and try to get through all 8 of these. They're starting out pretty easy, so hopefully everybody's hanging okay. All right, so remember, today I'm just looking for your right triangles to be set up and labeled correctly according to the scenario, all right? We're not having to solve for anything. All right, number 3. All right, let's read the whole problem in its entirety first to try to get a whole picture of what's going on. A telephone pole casts a 30-foot shadow. The angle of inclination from the end of the shadow to the top of the pole is 53 degrees. How tall is the telephone pole? All right, so I have a telephone pole that's casting a shadow. All right, so here's the ground. Here's my telephone pole. And it's casting a shadow, so I'm going to put the sun over here because then it's casting a shadow. So I'll just make this bold, like really dark. So here's the shadow. All right, so that's just kind of a picture of what's going on. We've got a telephone pole that's casting a shadow. All right, does that make sense to everybody? Hopefully so. All right, now let's try to take these numbers and fit it into our scenario, okay? So a telephone pole casts a 30-foot shadow. So I know that the length of the shadow right here is 30 feet, okay? From the end of the telephone pole out to the end of the shadow is 30 feet. The angle of inclination from the end of the shadow to the top of the pole is 53 degrees. So I can close that up. This angle right here is 53 degrees. The question is, how tall is the pole? So X would go right here. Okay, so we can extract this right triangle. This would be 30 feet, this would be 53 degrees, and that's what I would be looking for. So if we were to solve this problem, I would find my angle, my reference angle, and see what parts I have in relation to this angle. I've got opposite and adjacent, so I would use tangent on that one. And then I could easily find how tall that pole is. Okay, because you can't just like pull out a tape measure and, shimmy up a telephone pole. If you needed to know how tall it was, you would use math like this to figure that out. Okay, number 4 has a lot going on. This is a busy little problem. All right, so always read it in its entirety first. and so that you can start forming a picture, a scenario in your head. You don't want to just go straight to your paper, okay? You kind of got to get a scene developing. So, okay, a helicopter is hovering over a tree that is 100 feet from the center of the landing pad. The angle of inclination from the center of the landing pad to the helicopter is 42 degrees. How far will the helicopter travel from its current position to the center of the landing pad? Okay, so we have a couple of key things. We've got a tree, we got a helicopter hovering above it, and then we have a landing pad. So, so let's test our art skills. Megan can probably do these, a really fantastic, very detailed job at doing this. Mine will be very elementary looking, okay? So here's my tree. And then I've got a helicopter hovering above it. I really don't know how to make a helicopter. Okay. And then 100 feet from this tree, I've got a landing pad. All right, so I think they're usually rectangular, but I'm going to make mine circular just for the fun of it. Okay. All right, so now let's try to put some numbers in here and see if this makes sense. Okay, so a helicopter is hovering directly over a tree that is 100 feet from the center of the landing pad. So I know that this tree is 100 feet from the center of the landing pad. Okay, now the angle of inclination from the center of the landing pad to the helicopter is 42 degrees. Okay? Now, the question is, how far will the helicopter travel from its current position to the center of the landing pad? So how far will he travel to here? Okay, so we have the makings of, if I just drop down a vertical, I really needed this guy like right on top. So if I just drop down an altitude straight down from the helicopter through the tree, then I can close in this right triangle, okay? So let's just read through the problem and make sure that this makes sense. Let's make sure we didn't take a wrong turn. So we have a helicopter is hovering directly over a tree. The tree is 100 feet from the center of the landing pad. The angle of inclination from the center of the landing pad to the helicopter is 42 degrees. How far, that's your x, will the helicopter travel from its current position to the center of the landing pad? Okay? So does that make sense? You just have to kind of piece it together. Okay? Kind of got to get a picture in your head, try to put it on paper, go back to the problem, revisit the problem however many times you need to, okay, to fill in information, and then to make sure it makes sense. I have to make sure that my picture, my diagram here, actually fits the problem, okay? If it doesn't, I got to change my diagram, okay? I can't change the problem. So if we were to solve for this one, we would look at what we have. We have adjacent and we have hypotenuse, so we would use cosine, because cosine is adjacent over hypotenuse, right? All right, so ready to move on? That was number 4, so we're halfway done. Making good time, I think. All right, number 5. An airplane is taking off at 7 degrees at an airport. When the airplane is 1,388 feet from the runway, what is its altitude? Altitude means distance above like straight up, okay? All right, so we have an airplane. Airplanes, I think, are even harder than, it's got giant wings. He's taking off at, so here he is on the ground, and he's taking off, was it 7 degrees? Yes. 7 degrees from the airport. Okay. When he is, let me close this up. So this is the altitude. When he is 1,388 feet away from the runway, what is its altitude? So that's where your X would go, okay? Here's the runway, once he's this far from the runway, how high up in the sky will he be above sea level, okay? So that one's pretty simple. All right, number 6. All right, reading the whole thing. Let's get a picture in your head. Kevin is sitting on the edge of a fishing dock. His pole is 6 feet long, and he's holding it at an angle of 40 degrees. How far is his line from the dock? All right, so here is our image, okay? Here's the dock, and here's Kevin on the dock. Here's the water, and then here's his fishing pole, 6 feet, and it says that he's holding it at an angle of 40 degrees, so that, let me change this. This is kind of big to be doing this. My picture's kind of big. All right, so this is his pole, and no, we don't go by the picture. We never go by the picture. I know if this is 6 feet, he must be like 2 feet, okay? But we don't go by that, okay? You have to go by geometry rules. You just go by the facts. You go by the numbers. Don't go by my drawing because my drawing is off. Okay. Look, my line's not even straight. So you just go by the facts that we know. Okay. So here's the end of his pole. His line is dropping down here into the water. So the question is, how far is his line from the dock? So the X would go here. Okay. So this is what your right triangle would look like. Okay, so Kevin is sitting on the edge of a dock. His pole is 6 feet long. He's holding at an angle of 40 degrees. How far is the line from the dock? Okay? Not beautiful artwork, but it gets the job done. You got the triangle out of it. Okay. Number 7. All right, so let's read this one pretty carefully. All right, we got 5 minutes for each of these last 2 problems. Okay, Patty attached her paintbrush to the end of a pole so she could reach the corner of a wall and ceiling. Okay, so hopefully that makes sense. Like if I'm trying to paint there, I'm holding a pole so that my paint roller can hit between where the wall and the ceiling meet, okay? Now, it says that Patty's hand is 5 feet from the ceiling, okay? So that would be like saying my hand right here is 5 feet from the ceiling. and her pole is 7 feet long, okay? So you see my hand is 5 feet from the ceiling and the pole in my hand is 7 feet long, okay? How far from the wall is she standing? Okay, so this one is kind of tricky. So I think we're on 7 now. Is that right? Yes. Okay, so, okay, so let me try to make this make sense in a picture. Okay, so here's her hand. Okay, that's a really, really terrible hand. I can do better than that. 1, 2, 3, 4. Okay. Her pinky's just huge, but okay. So, and in her hand, she has a pole that's 7 feet long. Okay. And then, you know, on the end of it, you got a roller, paintbrush roller, okay? And it says that, so this roller is up in the corner where the wall and the ceiling meet. Okay, so here's the ceiling, and it's not terribly important, but just so that you can kind of get a, like this would be the wall, okay? It's not going to be part of our actual triangle, but just to kind of help you see, this is the wall. You can just use like a different color or something. There's the wall. There's the ceiling. And I know that her hand is 5 feet from the ceiling. So there's your right triangle, okay? The question is, so what we're looking for is how far from the wall is she standing? So she's here, and here's the wall, so that's this distance. So that's your x. Okay? That one might have been kind of hard to put together. Okay, so let's just make sure that this makes sense. Patty attached her paintbrush to the end of a pole so she could reach the corner. This is the wall and the ceiling where they meet. Her hand is 5 feet from the ceiling. Her pole is 7 feet long. How far from the wall, this is her, how far is she standing from the wall? So the distance from her to, it's going to be the same here and here. Those are going to be parallel to each other. Okay, so I can just close up that right triangle. All right? Okay, so it's just a right triangle that looks like this. So on this one, I would use the Pythagorean theorem to find out that missing. Okay, last one. Squeeze it in. Number 8. All right, so let's read through it really fast. Okay, a zip line is suspended between the tops of 2 buildings, okay? And one line is at an angle of 35 degrees from the top of the shorter to the top of the taller. The difference between the buildings' heights is 40 feet. How far apart are the buildings? Okay, so I've got a shorter building and a taller building. So here's my shorter building. Here's my taller building. Okay? And it says a zip line is suspended between the tops of the 2 buildings. So there's my zip line. And the angle, the line is at an angle of 35 degrees from the top of the shorter to the top of the taller. Okay, so what I need to do is close in this, make a right triangle. This is that 35-degree angle. Okay, so the zip line is at a 35-degree angle between the 2. Okay, the difference between the building's heights is 40 feet, right? So however many feet this is 40 higher. So the 40 will go right here. Okay, it's just, all it says is the difference between the two is 40. So he's 40 feet higher than this guy. And the question is, how far apart are the buildings? So that's that distance right there. Okay, so we have a right triangle we can extract that looks like this. So if I were to solve this from this angle, I've got opposite and adjacent, I would use tangent. Okay, so that's what we'll do tomorrow. All right, so tomorrow we're going to be setting up right triangles according to some given scenarios, but we're actually going to go so far as to solve them. So what I'm hoping is that I can at least get them set up with you, and then you can just do the math on your own. I mean, we may like try to do some together all the way through, obviously, at the beginning, but at some point, I'm going to stop going all the way to the end and then just try to help you guys get these set up, because that's the hardest part, really, is just getting the problem set up from the word problem to actually a math problem, okay? So I know our time is up. I know some of you guys have got to hit the Spanish class. So make sure, okay, just because we did all these together does not mean that you don't have to do the work, okay? So you still have to go through the labor of following along, putting everything on paper that I put on the board and turn it in. And that's how I know that you did it. You were with me, you were engaged in this, okay? And that you did your fair share of the work, okay? So it should be a 100. No reason that you shouldn't get 100 on this, but you still got to do the work. So I will see you tomorrow, and we'll take problems like this an extra step, all right?